So today, we're going to examine intersections of lines that are given in vector equations. Okay? Now, there's a couple of things that we're going to consider when it comes to intersecting lines like this, okay? The first thing we'll be considering is the angle between them, like the one problem you had on your IP, okay? The other thing we will be considering is identifying the point where two things intersect. And if we can identify that point, also trying to identify whether or not the two objects that are moving actually hit each other, or if one just happened to go past that point and then the other one went past that point. Okay? So there's a couple of things that we're going to be looking at in relation to intersecting lines here. Okay? Here's our basic information about vector equations of lines to start with. So let's take a look at angle between vectors. Alright, here we have two lines, or not angle between vectors, angle between lines, which we're going to find by taking the angle between two vectors. Okay? Now you'll notice here we have two lines, R and S. And one thing I want to point out here is notice anytime we're dealing with more than one line, we need to use different parameters. Don't use T for both of these. You could use like T1 and T2 if you want, or you could use T and S, or really any letter you feel like. Just don't use the same thing, because if you use the same thing, it's going to be easy to assume that they are going to be at their positions at exactly the same time. And that's not always the case, as we'll see later on. Alright, but here when I want to look at finding the angle between two lines, I need to find the angle really between their directions. Okay, so I identify the direction vector for the one line. We'll call this one U. And we find the direction vector for the second line. We'll call this one V to match our formula below. And then we're just going to find the angle between these two vectors. Okay, this is something that you guys have done a number of times, just not in this context. Okay? Now, as we've seen before, when you find the angle between vectors, it's possible for that angle to be acute or obtuse. All right? We always took the angle that was between 0 and 180. Okay? So for example, this angle might be 100 degrees, this might be 260. We always said the angle between the vectors was the 100. All right? And this formula always gave us that. The difference here is that because we actually have lines intersecting like you see up here, it's possible you might get this obtuse angle up here. But when we're talking about the angle between two lines, we always give it as an acute angle. Alright, so if you happen to get an obtuse angle from your calculator after using the formula, just subtract it from 180, give the acute supplement to it. Alright, so we find our dot product. Now we're ready to, we know what we're doing, we're going to actually find our angle. What would the dot product be of these two vectors?
Negative 24.
Negative 24?
Yeah.
Okay. You get, hang on, negative 2 times 1, right?
Wait, of which two? Of the top of
12.
R and R. Oh, never mind.
What two vectors are we using?
Negative 7.
Okay, how are you getting that?
What do you mean dot product?
No, negative 2.
Yeah, I know.
12, 5.
Okay.
I multiplied and added.
We multiply and then add. So negative 2
Negative 12 and 5.
minus 12 plus 5. Okay, good. So that's negative
7.
9. Okay. Alright, so we have negative 9. That's our dot product over the product of the magnitudes. So if we have the vector negative 2, 3, 1, we're going to be taking the square root 4 plus 9 plus 1. Okay, so the square root of 14. 15, yeah.
Oh, no, sorry.
No,
You're right,
14.
you're right,
14.
Sorry.
And then we also take the square root of 1 plus 16 plus 25. So that's 42. Okay? So that is the cosine. By the way, I already know I'm going to get what kind of angle.
Cute.
Negative.
Negative angle.
Second quadrant.
Come on. Cosine is negative, so it should be second quadrant. It's going to be an obtuse angle. So I already know that to give the angle between the lines, I'm going to need to subtract my answer from 180. Okay? So when I do the inverse cosine, theta is inverse cosine of negative 9 over square root of 14 times square root of 42. And what do you get for theta? Okay. 111.8. So now we take our answer here, we subtract it from 180, and our actual answer is 68.2 degrees. Okay? There's our actual answer. Listen, one of the reasons why you guys need to be practicing doing this on your calculator is this is a really easy one to mess up when you're typing it in. Because you can get an error. Alright, because some of you might plug it in like this. Cosine inverse, you plug in negative 9 divided by square root of 14 times square root of 42. What's wrong with that? Why is that going to give you an error?
Because it's going to divide negative 9 by root 14 and multiply it by 42.
Okay, yeah, it's going to multiply that by root 42 instead of being divided by a negative root 42. That's going to give you an error because...
You can't have a radical in the denominator.
You can.
Because it's going to be greater than 1.
Because you're taking the inverse cosine of something bigger than 1. Okay? So when you get an error that ought to, stick out to you, oh, did I miss a parenthesis? Or another alternative would be simply to, since it's two radicals multiplied together, you can just make it the square root of 14 times 42. That's another alternative to make sure they're both in that denominator. Okay? So just be careful using your calculators. Okay? Alrighty. So, that's finding the angle between two lines. Always in an acute angle. The other thing we want to look at, though, is determining not what angle two lines intersect at, but what point they intersect at. Okay? Here we have two lines. We have the vector equation xy equals negative 2, 1 plus s times 3, 2. And line 2 as the equation xy equals 15, 5 plus t times negative 4, 1. Okay? Now, these two equations are two different lines. In order to be in the same location, their positions have to be equal. Okay? So the intersection point where the lines meet is going to be where this equation equals this equation. So you'll notice that's what I just did here in writing this negative 2, 1 plus s times 3, 2 equals 15, 5 plus t times negative 4, 1. Okay? So we set the two equations equal to each other. You might say, well, that's real nice. Now what? Okay? Here's where the parametrics come in. All right? Let's look at this in terms of the parametric equations. If I looked at the x equations, all right, x equals, for the first line, negative 2 plus 3s. Okay? What does x equal for the second line?
15 plus negative 14.
Very good. 15 plus a negative 4t, so minus 4t. Now, in order to be the same point, the x coordinates have to be equal. Okay? So as I'm looking at my parametric equations, I'm going to set the two x equations equal to each other. Now I'm going to do the same thing with my y's. Okay? For the first line, what does y equal? 1 plus 2s. Very good. And for the second line, what does y equal? 5 plus t. And what do we have here? A system of equations. Okay? We have a system of equations. So, you guys know how to solve systems of equations. You can do it by elimination, by substitution, however you prefer solving them. Okay? A lot of times it's not too hard to use elimination. For example, notice the x's have a minus 4t and the y's have a plus 1t. So if I just multiply both sides of the y equation by 4, notice what I'll end up with, okay? I get 4 plus 8s equals 20 plus 4t. If I bring over the other equation, I have a negative 2, that's a 4 by the way, a negative 2 plus 3s equals 15 minus 4t. And notice the reason why I multiplied by 4 is so that now I can add those two equations together and my t's will cancel out. I eliminated the t's. Alright, so we have a positive 2 plus 11s equals 35. I solve it and I get s equal to 3. Okay? Does everyone understand so far what we're doing? Okay. Now, technically speaking, I could stop at this point. Alright? If I were to stop at this point and I look at line 1, because line 1 is the one with the s in it. Okay? Here's line 1. Okay? I would do negative 2, 1 plus 3 times 3, 2. And what position does that give me?
Where did you plug that in? Where'd you get that?
I plugged it in for s. We just found what s has to equal. S has to be 3.
Oh, that's
Okay? So if I have negative 2 plus 3 times 3,
7.
I get 7.
And 7 on the bottom.
And also the y is 7. So I'm at the point 7, 7. Okay? So, assuming we did everything correctly, we've got the right answer. I do want to, though, confirm this by finding out what t would equal. Okay? So let's look at the value of t. Okay? If s is 3 and I go back to, say, this equation right here, I have 1 plus 2 times 3 equals 5 plus t. Okay? So 1 plus 6 is 7. 7 minus 5 is 2. So I know that t equals 2. And to confirm our point should be the point 7, 7, I'm going to use line 2 here. And I have 15.5 plus t, which is 2, times negative 4, 1. Okay? So 15 plus 2 times negative 4. 15 minus 8 is 7. And 5 plus 2 times 1, 5 plus 2 is 7. So therefore, these two lines intersect at the point 7, 7. Okay?
So that's line 1 and line 2, right?
Yes, I just showed that they both are going to hit the point 7, 7. So the
Okay,
system of
that's their
equations,
intersection.
yeah, the system of equations shows us when this is going to happen. And notice, here's a perfect example, guys. Remember at the beginning when I said anytime you're dealing with two different equations, use two different parameters? This is why. Because notice, line 1 reaches the point 7, 7 after 3 units of time, 3 seconds we'll say. Okay? Line 2, however, gets there a little earlier. It gets there at 2 seconds. Okay? So, if these were two objects, would they hit each other? No. Line 2, the object going along line 2 would pass. It would be at 0.77 while the other line was still on its way. Okay? So let's say we're at line 2. Line 2 would look something like this. Okay? And maybe here's the point 7, 7. But it's there when t equals 2. Well, line 1 is approaching it, but at t equals 2, or at time 2, we haven't gotten there yet. Okay? So that's kind of what's happening when line 2 gets here at 7, 7. Line 1 is still not quite there. It's on its way. Okay? And in fact, if we wanted the actual point, we would be at 4, 5. Okay? Then, by the time line 2 gets there, when s equals 3, okay? By the time it gets there, line 1 has already been passed, and it's over at, oh wait, I have it drawn wrong, but it would be at 3, 8. Yeah, this is not drawn correctly, but you guys get the idea. Okay?
If it was a 3D plane, they could have the same point, right?
They can.
And
It's a little more challenging to get them to hit each other, though.
Right, 'cause they would have to match them to the same point.
Well, actually in 3D, all 3 coordinates would have to be equal to each other. And in order for them to hit, they'd all have to be equal to each other at the same time.
Yeah.
Okay? In order, and that's true for any of these, in order for these things to actually hit each other, they'd have to both be at 7, 7 at the same time.
So, I get what you just said, but how did you figure out that, so you solved for s, and you got s equals 3.
Mm-hmm.
So then you plugged the 3 back into the y parametric equation, right?
Well, I plug it back into the first line where we have s. Right here, I put a 3 in for s. And that tells me our position after 3 seconds,
Okay.
or 3 units of time.
So then, when you have that little green arrow, you plugged in, you solved for t, right?
What, this right here?
No, right to the left.
Yeah, right here. Once I knew that S was 3, I plugged it in. That's how I got this right here. Okay, so 1 plus 2S equals 5 plus T. That's how I solve for T. So, I guess, to answer your question right, yes, I did plug this into the Y parametric equation in order to get T. I also plugged it into the first line in order to get that intersection point. So we used that 3 in 2 different places.
Okay, so after you plugged the 3 into the vector equation and you got 7, 7, where did you go from there?
Well, at that point we could have stopped. Okay? We could have stopped, we found the intersection point, assuming we did everything correctly. I kept going, in this case, to confirm our answer by finding what t is and plugging that into the second equation. Okay? It was just a matter of checking our answer right here. If I had plugged 2 in and I got something else other than 7, 7, I know I would have done something wrong.
So the lines don't meet.
No, the lines, here's the thing. You have to think of it in terms of their path versus an object moving along the path. Okay? We can see right here the paths do cross at the point 7, 7. If there were objects traveling along those paths, they would not collide with one another, because this object got here 1 second before this object did. Okay? So they just missed each other. It's kind of like 2 people leaving the room. You know, hopefully their times are not equal or else they're going to run into each other. But one person goes through the door first and then another person goes through right after them. That's kind of like what we had here. Here's our door. He's going this way, they're going that way. Okay? So, to address what we were just talking about, actually, did these lines actually cross? Did the objects actually meet? We just looked at a case before the one that we just did, the very first example we did where we found the angle between the lines. We were assuming that those lines actually crossed each other. But as you guys know, in 3-dimensional space, it's possible for 2 things not to be parallel, but not to intersect with one another either. Does anyone remember the term for that? They're not parallel, but they don't intersect in 3-dimensional space. Skew. Remember skew?
No.
It's kind of like if we had if we have a cube. I like to use this as an illustration because you can see it real well. Okay, here we have a cube. There's in the background. Okay. All right. So there's our cube. If I were to look at this line making up this edge right here, and this line making up the edge on the back side right here, do those 2 lines hit each other? No. Are they parallel? No. That's skew lines. Okay?
Ethan goes,
I thought for a second that they might have been.
They're not parallel. Okay, those are skew. Now, when we draw it on a 2-dimensional piece of paper, it looks like they're going to hit each other, but we know from our 3D perspective that that one is going to be going past it behind this one that's closer to us, all right? So, it's possible when we're dealing in 3D that these, while they are not parallel, the vectors, the direction vectors are not a multiple of each other. Okay, so they're not parallel. It's possible that they actually did not meet though. Okay? So, how do we tell if the lines actually do cross? And then secondly, if there were objects going along these paths, do they hit each other? Okay? So there's a lot that has to go right in order for them to actually hit each other. So let's look at this first of all. With R, let's look at our parametric equations. X equals what for R? Let's call them out quick here. X equals
12 plus negative 2t. 12
Good.
minus 2t.
12 minus 2t, alright? Y equals
Negative 15 plus 3t.
negative 15 plus 3t. I'm sure more than one of you knows this. Z equals
15 plus t.
15 plus t. Come on, some of you silent folks. Show me you know it, alright? Now, for line S.
3 plus S.
Okay. X equals 3 plus S.
6 minus 4S.
Y is 6 minus 4S.
3 plus 5s.
Z is 3 plus 5S. Now, how are we going to see if these lines actually cross? What do you think?
Did we just do exactly what we did before?
What do you mean?
With the previous problem, where you find the, where you plug them both in, like you create the system of equations?
Yeah, let's set up a system of equations. The nice thing about this is you can actually use any two that you want. We could use x and y, or y and z, or x and z. Doesn't matter. Okay, which ones do you guys want to use?
X and z.
X and z, alright. So 12 minus 2t has to equal 3 plus s. And z, 15 plus t has to equal 3 plus 5s. Okay? So we solve our system of equations, right? Go ahead and take a second and solve that. And here, by the way, you do need to get both s and t.
Okay.
We'll see why in a sec.
No, I'm different.
Alright? We got 3 for both of them? You got 2 and negative 2?
That's 6 and 18.
6 and 18? Maybe we need some practice with our systems of equations.
I got 3 for S, I'm still solving for
You got 3 for s?
I got 3 for
You got 3 for both?
Yeah, because if you plug it in, it works.
Alright, good. We should have gotten 3 for both, okay? We should have gotten 3 for both. Now that we unfroze the screen here, you can see it. Alright, S equals 3, T equals 3. Check your arithmetic if you didn't quite get that. Alright. Notice what I did here. I saw I had a minus 2t and a plus 1t, so I just multiplied this second equation by 2. So I had 12 plus 30 is 42. Negative 2t plus 2t is 0. 3 plus 6 is 9. And s plus 10s is 11s. And then we solve from there. Okay? Now, this is why I want to make sure that you find both of them. Okay? We never did use the y equations on this, did we? Alright? It's possible that the two lines are at the same values of x and z, but their y's are different. So you need to find both times. So stay with me here real quick. R, if t is 3, then r is going to be 12 minus 2 times 3. Well, that's 12 minus 6 is 6. Okay? Negative 15 plus 3 times 3 is 9, so that's going to be a negative 6. And then 15 plus 3 is 18. Okay? Then we have line S. If I plug in S equals 3, 3 plus 3 is 6. 6 minus 12 is a negative 6. And 3 plus 15 is 18. So, did the lines cross?
Yes.
Yes. Did the objects meet?
We don't know.
We do.
No. Maybe.
Yes, because the
times the same?
Yes, because the times are the same. So here's the deal. They can get the same point, but be at different times. Then their paths crossed, but they didn't actually meet. If we want them to actually hit each other, they got to be at the same point at the same time. Okay? So, did they cross? Yes. Did they meet? Yes. Okay? It's cool stuff that we can do with this, alright? We'll see you guys. Have a great weekend.